Bayesian inference is the first decision fusion technique we are going to deal with in this presentation. In this slide, we are going to see how we can apply Bayesian inference in decision fusion context and the Bayesian network, which are a framework that hold on the application of the Bayesian inference and is particularly useful for time evolving state. So the Bayesian inference in this context is used to determine the value of a categorical state and given some evidences which are provided by our sensor data. So data that we can measure. I want to underline two main concepts. First of all, the state here is categorical. So it basically assumes value in a finite domain like 0, n. So this is the value that our state can have. This is important because this is the main difference between the this kind of Bayesian inference and the one we see before the state estimation, where the state was a real number. Basically, as we said in the introduction, decision in mathematical term mean classification. So we want to know the state of a person. Is the person ill or is the person without no problem? Is the person running or is the person laying on a bed? So everything that can be categorized. And also I want to point out about the input, so the different sensor data. In a decision fusion context, such data will be categorical as well. So we will deal with the sensor that outputs a state as well, as we will see later. First of all, in the right part of the slide here, you will see the application of the Bayesian rule in a sensor fusion context. So our posterior probability is what actually we want to optimize. And this is the probability of the hypothesis. So with hypothesis, we see hypothesis that x, the state, is equal to 0, the hypothesis that x is equal 1 or is n, given the data, given the evidences we have measured in our system. And we want to optimize this, but this is achievable, this function is achievable only through this calculation given by the Bayesian rule. The likelihood here represents the probability of the data given the hypothesis. And this is what we can measure in a real context. Basically, the probability that we measure such data given the fact that we knew that we were in a certain state. And then we have the prior probability, which is the probability given by a previous knowledge that actually we are in that state, and the evidence, which is the probability of the data. So this is the Bayesian rule. What are the Bayesian networks at this point? Simply, as we said, the Bayesian networks are application of the Bayes rule for a time evolving system. So instead of having a single x, here we have a x of a t. And so we have a state that's vary in time. Specifically, in a sensor fusion context, a situation is very similar to the one depicted in the picture here on the bottom. So we have a state x that is evolving in time, as we see here, and for every time we have a set of evidences given by the sensors. So the inputs to our system is actually the evidences given by the sensor, which will be, as we said, it will be categorical, and a likelihood function for each of the for each time. So the probability of the evidences given the fact that we knew the state. And optional, as we will see later, we can have sometime even the transition probability. So the probability that we know we are in a state, in a time t, in a certain state, given the fact that we know that in the time t minus 1, we were in another state. So this is we call a specific case of Bayesian network called hidden Markov model, but we will see this later. As we said, the output, what we want is an estimation, a categorical escalate again, x of t. So now we have all the context. Let's see an example. A great example of application of Bayesian inference and Bayesian networks in health tech technology is provided in what we call the ambient sensing context. So ambient sensing can be defined as a specific branch of smart assisted living which deals with the detection of a context, of a certain context given through a set of sensors placed in an indoor environment. So this context can be different. I mean, we can have different type of context. For example, we can be interested if a user is in a room, so he's occupying a room, or we can be interested in the health status of the user, or, for example, to determine an anomalous status such as a loss of consciousness or a fall, or the presence of an intruder, for example. I mean, kind of application. Ambient sensing has a great application in smart assisted living, particularly for the monitoring of fragile people and elder people. So the specific example I want to discuss with you today in this course actually is given by this paper down there, which I strongly suggest to read for who is interested. So the title is Multi-Sensor Fusion through Adaptive Bayesian Network. So the aim of the paper, the goal, is to determine if a user is occupying a room in a given moment. For this reason, this definition of the state is quite trivial, and actually the state X can be 0 if the person, the user is not in the room, or 1 if the person is in the room. This is done through our input, which is sensor input. Of course, we are dealing about sensor fusion, so the input are sensor, and specifically 3 types of sensor. We have a door sensor, which determine the state of the door, if the door is locked, closed, open, 0, 1, 2. A software sensor, which is actually the personal computer of the person, which can be open or on off, and a sound sensor, measure the sound, the amount of noise in the room, and give us in output a state, which is in the room or not in the room. So in the picture here on the bottom right of the slide, we see how this can be considered as part of a Bayesian network. So at time t, we have the state x of t, which provide us the presence or not presence of the user in the room. And this is what we want to determine. This is the goal of our of the Bayesian network, the state. And the evidences in this case, the E of t, are provided by the sensor. So we have the sound sensor, the door status, and the software sensor. So in this slide, we are going to see how a Bayesian network can help us in our target. So with the aim of determining the value of the state at time, this is time t, we built a belief function, which is actually the posterior probability. So given the evidences that we measure from the time 1, so the starting of our sensing, to the time t, we take all the evidences, this one, which is actually what we have access to. So this is sort of the probability of the state x of t given all the evidences. And as you can see here, this is a function actually. So it's a vector, no? So given the fact that we have 2 states, this one would be we have the belief of the state is 1 and the belief that the state is 0. And what we want to do actually is to find the state which maximize our belief function, so which maximize the posteriori probability that we are in the state x of that the state x of t is as this given value given all the evidence before. And here we see in the structure of this network. No, we have the state of x0, which is connected to the state x1, state x of t minus 1, and state x of t. And actually, what is the main problem at this point? The problem is the fact that this function is incredibly complex to calculate. And we will see in the next slide how to deal with this complexity. So in this slide, we are going more in deep in how we can build and use a Bayesian network for our purpose. First of all, in the previous slide, we have defined the belief function, which is, we said that we want to maximize this posterior probability in order to find the best value of the state x of t. If you remember the first slide of the Bayesian, on the Bayesian inference, we said that the Bayes function, the Bayes formula, which is the likelihood multiplied by the prior divided by the evidences. In our cases, we have no distribution on the data and no particular distribution on the value of the state. So the prior and the evidence are not considered. So in this case, what we can say is the fact that the posterior probability is equal to the likelihood. So our problem is now focused on find this likelihood. And actually, this likelihood is calculated in the first step, in the training step, where we use a dataset to calculate the value of this likelihood, which is represented by this table. Just to be more specifically, for the sensor 1, what does it mean, the likelihood function? So the sensor 1 is the door sensor. It can be open, closed, or locked. So what we have done here is going through the data, monitor the user, and see that when actually the user is out of the room, so the state is 0, 20% of time we have the sensor in the state 2, so the door is locked. The 30% of time the door is closed, and the 0% and the half of time the door is open. And we did this for all the other sensors. So in this way, we have built this table, which is actually represent our likelihood, and at this point, we are able to calculate the posterior probability. The main problem is represented by the fact that we are in a Bayesian network. So the belief at time t is not only dependent on the evidences at time t, so this one, but is dependent also on the evidence at time before t. Here. So there is a huge theory used behind the Bayesian network for how to calculate this belief function. In our case, we did what we call the Markov assumption. So in this case, is say that the value of the belief function of the state at time t is conditioned only by the knowledge, our knowledge on the state t minus 1, and on the evidences at time t. So applying the Markov assumption, we can see that we can build our belief function in the two main blocks. One is basically the dependent on the evidences at time t, and this actually is exactly the multiplication of all the likelihood, and the belief function at time minus t1. There is another term here, which is what we call the transition probability, the probability that of the state at time t is given the fact that we are in the state t minus 1. So this is again calculating the training phase, and this is the table down here, and it's actually extracted from the data. So what we have seen is the fact that if we were in 0 at t minus 1, we have the 80% of probability that we are still in 0 at time t. So in the bottom part of the slide, we provide an example how a Bayesian network can be operative use to our targets. So we start at time t equal to 0, where we have a previous kind of knowledge on the state, because we have 0.9 probability that the state is 0, so the user is not in the room. At time equal to 1, what we do is reading the sensor output, so reading the evidences that come from the sensors. Again, in this case, it's not a direct measure, because what the sensor provides us is a state, is a categorical state. It's not a direct measure, because remember that we are in the decision fusion context, so we are trying to fuse, mathematically speaking, output of classifier. So we calculate the belief function x1 on the state x1. And as you can see, it's 0.9 for state 0 and 0.09 for state 1. Applying the argmax, we conclude that the estimation of the value of the state at time equals 1 is 0. And here we have the result. So I really hope that through this explanation, you have been able to understand how Bayesian inference and this kind of empowered version of Bayesian inference, which is the Bayesian network, can be easily used in a decision fusion context. And most of the technologies that actually try to predict, for example, anomalous states, for example, in the smartwatches, most of them hold on Bayesian approach like this. On the next slide, we will see how this Bayesian approach can be overcome